Okay, how'd we do? Good? Review? We're good? We're happy? We know when you can use this. Homogeneous constant coefficients. We talked about distinct real roots and complex roots last time, and so the case we still have to deal with is repeated real roots. Yes? Good? Everybody's good? Okay, so section 5.6, whiteboard here. If I never have to share a whiteboard in Zoom again, it is going to be too soon, I swear. This is just, I want a chalkboard, I want chalk, I don't even care if my hands are gonna be dry, it's fine, I am done with this. Hi, section 5.6. So, is multiple eigenvalue solutions. All right, I'm gonna give you, it's not exactly a definition, it's more like a concept, and it's gonna be a concept that doesn't make a lot of sense until we do some examples. So concept of multiple or repeated roots, we should say repeated roots instead, not multiple. Our concept of repeated roots is that there are two types. Type number one is not defective. And this is good. We like this case. This case makes us happy. Type number two is defective. And this case does not make us happy. This is a sad case. If we have, I'm talking in generalities, and then I'm going to do an example and it will make way more sense, I promise. If we have not defective, if we have a repeated root that is not defective, then we can find enough linearly independent eigenvectors. So we can, this is good, this is why it's happy, find enough linearly independent eigenvectors. And what that means is that we can, again, this is the happy case, so can find a general solution. This is good. This is the happy case. We like the not defective case. This is good. The defective case comes in when we cannot find enough linearly independent eigenvectors. So that's the sad case. We cannot find enough linearly independent eigenvectors. I'm not going to say cannot find a general solution because we can, but what we have to do is need a different method to find a general solution. And I don't think we're going to get to this different method today. I think that's going to be the very last thing that we talk about this semester tomorrow. So we need a different method to find a general solution. We still can, it's still doable. We just can't use the same process that we've been talking about up to this point. So then the question is, how do you tell? How do you tell when you have repeated roots, whether they are defective or not defective? How do you tell if we're in the happy case or the sad case? And for that, we need to talk about something called free variables, which my linear algebra people should be very, 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 very familiar with. So here's my actual technical definition, and there's going to be some words in here that you don't know. That's okay. An eigenvalue, because remember these repeated roots come from the eigenvalues, right? So an eigenvalue is defective if the algebraic multiplicity, you don't know what these words mean yet, and that's okay. The algebraic multiplicity is greater than the number of free variables. You don't know what algebraic multiplicity is, you don't know what number of free variables is, I promise that we'll get there. I'm okay with that for right now. So an eigenvalue is defective if the algebraic multiplicity is greater than the number of free variables. Algebraic multiplicity is really easy to understand. So algebraic multiplicity is just the number of times the eigenvalue appears as a root. That's easy. Eigenvalue appears as a root. The number of times the eigenvalue appears as a root. That's easy, that's no big deal. You just gotta count up, do I have a linear factor squared? Do I have it cubed? How many times does it show up as a root? We're very good at this. We did this back in chapter 2, no problem, no big deal. That's algebraic multiplicity. Number of free variables is a little bit harder to summarize succinctly, so I'm going to do an example and help you figure out what number of free variables is. That one's easier to get as a concept through an example as opposed to having me put a definition down for you. So let's do this one. I'm going to jump right to the matrix instead of the differential equation. So let's say that my matrix A looks like this, and I'm reading across 2, 0, 0, negative 7, 9, 7, 0, 0, 2. Okay, and remember that this comes from vector x prime equals a times vector x. I'm just jumping into, we've already found the matrix. Are we okay with me jumping into, we've already found the matrix? All good there? All right. We're going to do this one start to finish because I think I assigned some 3x3s on your homework, and we haven't done a 3x3 finding the eigenvalues yet. So let's do this one start to finish. So 0 is going to be determinant of lambda I minus a. You should be getting comfortable with this equation by now. So that's going to be the determinant of lambda minus 2, 0, 0. That negative 7 has to change to a positive 7 because you're subtracting, right? Lambda minus 9, negative 7, 0, 0, lambda minus 2. And then remember how we take the determinant of a 3x3 matrix. This is the cornfield method, corn rows. So we've got lambda minus 2, 0, 7, lambda minus 9, 0, and 0. I think, oh, I can change my pen color. So let's go forwards with pink. It's just like color chalk in the classroom. There we go. Forwards with pink. The small things are what get you excited today. I'm gonna go backwards with green. See, this I couldn't have done on day 1 of Zoom teaching, but now we can. Backwards with green. Here we go. It's the little things. And there's a whole ton of zeros in here. So what you're gonna end up with is lambda minus 2 squared times lambda minus 9. Everything else has a 0 in it. Lambda minus 2 squared times lambda minus 9. So here's my eigenvalues. My eigenvalues are going to be lambda equals 2, 2, and 9. All good? Besides the fact that you gotta remember how to do a 3x3 determinant. We're good? Everybody's good? Okay, so now let's talk algebraic multiplicity. For lambda equals 2, the algebraic multiplicity is equal to 2 because lambda equals 2 shows up twice as a root. Like I said, algebraic multiplicity is super easy to find, no problem. For lambda equals 9, my algebraic multiplicity is equal to 1 because lambda equals 9 shows up once as a root. Are we doing good? Everybody's good up to there? Everybody's good? I'm getting some thumbs up, some nods. Okay, cool. All right, let's go ahead and look at that second part, that free variables part that I haven't explained yet. So let's do lambda equals 2 first. So if we do lambda equals 2, we're gonna plug that into my matrix. Same thing as with the 2x2, it's just bigger. So I am going to get, we're doing lambda equals 2. Sorry, this is where I wish I had more chalkboard. Reading across 0, 0, 0, negative 7, 7, 7, 0, 0, 0. Right? And what I want to do, same process as before, we've just got more entries to zero out, is zero out the entries in the bottom left in order to make this in triangular form. Same process as before. I can just swap row 1 and row 2, and then I'm totally going to get right into triangular form. We're going to do another example where you got slightly more involved row operations, but for this one, it's nice and easy. What did I screw up? Because 2 people just raised their hand. Zach?
Isn't it 7, -7, -7?
Yes, I am backwards because my notes are backwards. Thank you. 7, -7, -7. Thank you. Okay, row 1 and row 2 can just get swapped. So row 1 gets swapped with row 2. And then what I am going to get is 7, -7, -7, 0, 0, 0, 0, 0, 0. So I've zeroed out the entries that I'm looking to zero out. We've gotten to this triangular form. And remember what I'm trying to find is a vector v. So again, one more time, we'll label these columns v1, v2, v3. Those are my components in the columns. All right. In order to figure out how many free variables there are, we have to figure out how many leading variables there are. So my leading variables are the ones that have a non-zero entry in the column associated with them. In this case, it's just V1. My leading variable is just going to be V1. V2, this isn't a leading entry because there's something to the left of it, and the rest of the leading entries are 0. So V2 is not a leading variable. Same thing with V3. This -7 is not a leading entry because there's non-zero entries to the left, and the rest of the entries are 0. So it's easier to identify leading variables first, and then my free variables are the other ones. So my free variables are V2 and V3. Okay, leading variables, free variables. So in this case, for lambda equals 2, the algebraic multiplicity is equal to 2, right? That was on the previous slide. And the number of free variables is also equal to 2. We're seeing both of those, pulling them back together. Algebraic multiplicity is 2, number of free variables is equal to 2, and therefore this tells me that lambda equals 2 is not defective. That's good. We like that. That makes me happy. Lambda equals 2 is not defective. Nod at me, give me a thumbs up, tell me that that part makes sense. Doing good? Doing good? Okay, all right. For lambda equals 9, I could totally repeat the process, and I'm gonna have to when I'm trying to find my eigenvector, but here's the nice part. For lambda equals 9, I know that my algebraic multiplicity is 1, right? That was on the previous slide. I can go back to it if I have to, but my algebraic multiplicity is equal to 1. I also know 2 things. I also know that the number of free variables is always positive. I always have at least 1 free variable when I'm looking for eigenvalues. So I know that my number of free variables is always positive. And I know that my number of free variables is always less than or equal to my algebraic multiplicity. If you take linear algebra, we prove both of these things. In here, we're just stating them. So number of free variables is always bigger than 0 and less than or equal to the algebraic multiplicity. For this example, then, I know how many free variables are, right? Fingers, hold up fingers. How many free variables do there have to be for this particular one? Holding up fingers for me, there have to be 1, yes, 1, okay. And so therefore, I have to have the number of free variables equals 1. And so this is also not defective. That's good. We are going to swing back to this example and finish it, find a general solution, but first I want to do another example and show you how eigenvalue can be defective. All right, so we're going to swing back to this one, but I want to do another example first. Daniel, question before that.
Can't we also just say that the number of leading variables is always greater than or equal to 1, as long as it's not like a 0 matrix?
Yes, yep, and that's why you know that the number of free variables is always less than or equal to the algebraic multiplicity.
Oh, yeah.
Yes. Yep, exactly. Same idea, different way of saying it. Yes. Abby, question.
So if they equal each other, the algebraic multiplicity and the free variables, then it's not defective?
Correct. Is that what I said on the previous slide? Or did I say it backwards?
Oh, I didn't look, sorry.
2 slides back. Let's see.
Probably right.
Effective if the algebraic multiplicity is greater than the number of free variables. So the opposite to that would be if they equal each other, then not defective.
Okay, okay,
Yes.
thanks.
Good. Other questions? Stuart, yeah.
Could you just go back through how you're finding the leading variables? That's just the first one in its row, right? The first
Yes,
variable.
let me do another example and I think it'll help with finding leading variables. Okay. Other questions? Anything else? Good questions so far. Other ones? Okay, let me